On September 23, 1999, a multi-million-dollar spacecraft, designed to study the Martian climate, disintegrated in the planet's atmosphere, not due to cosmic rays or mechanical failure, but because one team used imperial measurements where another expected metric. This single, seemingly innocuous discrepancy, a wrong number in the vast symphony of interplanetary travel, sent the MarsClimateOrbiter spiraling into an unforeseen oblivion. The mission began with boundless optimism. Launched in December 1998, the MarsClimateOrbiter was a crown jewel in NASA's faster, better, cheaper initiative. Its purpose was ambitious: to circle Mars for 687 Earth days, meticulously studying the planet's weather patterns, atmospheric composition, and surface changes. It carried advanced instruments, designed to provide unprecedented insights into how Mars transformed from a potentially water-rich world to the arid landscape we know today. Thousands of hours, millions of dollars, and the hopes of an entire scientific community were invested in this solitary probe, destined for a distant red world. As the orbiter sailed through the cold vacuum of space, its journey was a ballet of precision. Navigation engineers on Earth constantly tracked its position, firing tiny thrusters to make subtle course corrections. These burns were crucial, pushing the spacecraft along its precise trajectory, nudging it toward its final orbital insertion point around Mars. Every adjustment was calculated with painstaking detail, a complex equation of mass, velocity, and force. The primary team responsible for the spacecraft's trajectory was based at NASA's Jet Propulsion Laboratory, or JPL, in Pasadena, California. They were the conductors of this interstellar orchestra, guiding the probe with invisible hands. They relied on data from another team, Lockheed Martin Astronautics in Denver, who built the spacecraft and managed its operational systems, including the crucial thruster firings. This division of labor, common in large-scale space projects, required seamless communication and absolute consistency in data interpretation. Here, a subtle but fatal flaw began to propagate. Lockheed Martin's engineers, when calculating the force exerted by the thrusters, used the standard American unit of pound force for their impulse data. This seemed logical to them, as their software and internal processes were designed around these units. However, the navigation team at JPL, whose trajectory models were built upon an international standard, expected this data in Newton seconds, the metric unit for impulse. It was a silent, unacknowledged language barrier between two highly sophisticated technical teams. For months, as the orbiter hurtled through the void, these mismatched numbers were fed into JPL's navigation software. Every time Lockheed Martin provided thruster performance data in pound seconds, JPL's system interpreted it as Newton seconds. 1 pound force is approximately 4.45 newtons. This meant that every thruster firing was effectively considered by JPL's software to be only about a quarter as powerful as it actually was. The impact of this discrepancy was not immediately apparent, a slow-burning fuse in the intricate mechanics of space travel. As the spacecraft neared Mars, the cumulative error became undeniable, though its cause remained a mystery. JPL's navigation team noticed that the orbiter's trajectory was consistently lower than predicted. Each course correction, each command to fire the thrusters, seemed to undershoot its target, requiring more frequent and larger adjustments. They attributed this to slight variations in solar pressure or other minor environmental factors, performing a series of small, incremental course corrections to lift the probe's predicted path. This was the system attempting to compensate, unknowingly, for a fundamental misunderstanding. Weeks before arrival, the tension mounted. Mission controllers knew the precise altitude required for orbital insertion, a delicate balance between catching Mars' gravity and avoiding its destructive atmosphere. The nominal altitude was 226 kilometers, roughly 140 miles above the Martian surface. If the orbiter dipped too low, it would burn up. If it flew too high, it would skip off the atmosphere and be lost to deep space. The margin for error was razor thin, a mere few kilometers. On September 22, 1999, the MarsClimateOrbiter reached its final destination. As it plunged toward Mars, controllers watched the telemetry data. The spacecraft was scheduled to perform a critical engine burn, slowing itself down enough to be captured by Mars' gravity and settle into orbit. But the data coming back was alarming. The orbiter was entering the atmosphere far too low. Instead of the planned 226 kilometers, it was hurtling towards the planet at an estimated 57 kilometers, or just 35 miles, above the surface. The last telemetry signal from the Mars Climate Orbiter was received at 2 hours 0 minutes and 46 seconds AM Pacific Daylight Time. It was precisely at that moment the spacecraft, traveling at nearly 12,000 miles per hour, began its fatal plunge into the Martian atmosphere. The extreme friction and pressure would have instantly superheated its structure, tearing it apart. The probe was incinerated, vaporized into cosmic dust. The controllers waited, then waited longer, for a signal that would never come. The silence in the control room was deafening, a stark monument to a mission irrevocably lost. The post-mortem investigation was swift and brutal. Within days, the shocking truth emerged. It was not a hardware failure, not a meteoroid strike, and not a software bug in the traditional sense. It was human error, a breakdown in fundamental communication. The precise calculations that had guided the probe across hundreds of millions of miles were undone by a simple, yet catastrophic, unit conversion oversight. A small team, part of a larger project, had failed to convert imperial pounds force to metric newtons in their data transmissions, rendering all subsequent navigation calculations critically flawed. The cost of this single, seemingly insignificant error was immense. The Mars Climate Orbiter mission had cost NASA $125 million, a significant sum then and now. But beyond the financial loss, there was the loss of invaluable scientific data, years of research, and the unquantifiable blow to morale. The scientific community had eagerly anticipated the orbiter's findings, especially its role as a communications relay for the Mars Polar Lander, which was scheduled to arrive just 2 months later. Without the orbiter, the lander's mission was also severely hampered. The story of the Mars Climate Orbiter became a stark and enduring lesson for NASA and for the entire engineering world. It highlighted the critical importance of meticulous attention to detail, robust cross-checking systems, and unambiguous communication protocols in complex, high-stakes endeavors. In a system where thousands of tiny decisions intertwine, the smallest oversight can unravel the grandest plan. The vacuum of space is an unforgiving arena, where even a wrong number, overlooked in a sea of data, can transform a triumph of human ingenuity into an expensive, silent memorial. The void, it seems, demands absolute precision.